Let's solve for the integral of the given function here along your contour C, which is bounded by 0 for your x until 1 and for your y 0 until 2. But this time, let's use here the Green's theorem in the plane. Now, in order for us to do that, let's not forget that for this to be applicable for Green's theorem, we need to identify, okay, this one here, the double integral along a certain region for your partial derivative of your q function with respect to your x minus the partial derivative of your p function with respect to y. You have here dx and dy. Of course, we need to identify first your q and p of x functions. Your p of xy will be the function situated as a product with dx. That's this function here. That's actually x squared y plus 2y. As for your q of xy, it's the other function paired with dy. That's actually your x y squared plus 3x. So we are going to solve first for the partial derivatives of both with respect to their corresponding variable. At the same time, we're going to use these regions as we're going to take the double integral of the result. So let's start first with the partial derivative. Allow me to use here this color. The partial derivative of your q function with respect to x. That's actually the partial derivative of whatever your q is. That's actually x y squared plus 3x. Take note, we are taking its partial derivative with respect to x. So those variables or terms with y, speaking of this one here, will be treated as constant. In short, y squared will be treated as a constant and x is your variable. And if this is your constant, okay, that would mean its first derivative for the first term is just y squared. As you, of course, you are taking its first derivative with respect to your x. Okay? Now, what would be for the second term? Take note that this also has x, so plus 3x would become plus 3. This is its partial derivative for your q function with respect to x. We'll be plugging that in here later. Let's just simply continue and solve for the partial derivative of your p with respect to y. This would be the partial derivative of your p function, which is x squared y plus 2y with respect to, sorry, that's not d, with respect to y. So again, x squared here will be treated as a constant. So with respect to y, that's actually just x squared. And this one here also has y. You have here plus 2. So these two functions will be plugged in here to our double integral. Okay, double integral on our region. As of the moment, let's call it region R. So you will have here for your partial derivative of q with respect to x is y squared plus 3. Then minus for your partial derivative of your p with respect to y. Again, it has a parenthesis because it's a grouping symbol. You have here dx and dy. Or simplifying that, you have the partial derivative, the double integral, sorry, for your rearranging them, minus x squared. Let's start with y squared if you would like to. You have here y squared minus x squared, and that's 3 minus 2 because of the grouping symbol, plus 1 dx and dy. Okay, so hopefully it's clear until this point. The next task for us to do here is to identify the boundary for your x and y, as we have here the region which is already identified here. If we're going to look at it in our Cartesian plane or any plane, you would see that this is a rectangular region from x moving from 0 to 1 and your y 0 to 2. And take note here, it's specific that your x would be from 0 to 1 and your y would be from 0 to 2. So if we're going to continue that here, if we're going to have here 0 to 1, that would mean this is the integral for your x. If you will have here 0 to 2, that's your integral for your y. So if we're going to continue this, y squared minus x squared plus 1, it is right to assume that you will have here dy dx rather than this, because the innermost integral here, which corresponds to this region, 0 to 2, corresponds to your region for your y. Okay? That's why we arrange it dy and dx. But of course, take note that our regions for x and y are specific. We can actually attack this in two different ways, and I can guarantee you that you will have the same result. If you would like to start here with dx and dy, take note that the regions here for your integral, or the integral symbols, would be interchanged as well. Now in the previous video, we have a square. Please try to look into that because we also have the example for that. And we actually used dy and dx. If I'm correct, we started with y before we proceed with x. Since this is still okay, similar to the idea of a square, this time is a rectangle where their boundary for your x and y are specific, allow me to attack this differently. Instead of dy dx, as similar to the previous video, let me have here, okay, I'm gonna stick with dx and dy, thereby rearranging this correctly. Because if we're going to start with dx, take note that x is 0 to 1, so you have here 0 to 1 and y 0 to 2. Again, if you will have to attack it the same as earlier, so you can actually have the same answer as this. So I'm gonna leave that to you to verify. So I'm going to talk about this first. Let's try to solve that first, and whatever the result of that integral, plug that in for these two boundaries here, our boundary and your dy. So let's start with this. Take note that if we're talking about dx with respect to x, all the y variables would be constant. I'm talking about this one here. So by linearity property, just for this, okay, by linearity property, y squared would be a constant. So you will have your integral of your dx from 0 to 1. You have minus, you will have to retain x squared here because that's with respect to x, 0 to 1. And as for your 1, you can bring that out, or simply you will have here integral of dx is 0 to 1. Again, we're talking about this one here, so this dy together with this integral sign will be treated later. Okay, so with that, after applying the linearity property, of course we know this to be y squared, and the integral of dx is just x itself. Take note, it's from 0 to 1. Similarly, for the second, take note that the integral of x squared is x cubed over 3, and you have here 0 to 1. And again, similar to the first term, the integral of dx is x from 0 to 1. These boundaries will be applied to x. So this y here will again be treated as this 1 and 0 boundary will be for x here. So if we're going to look into that, it will be in this step here. Y squared, you will have here 1 minus y squared, 0. For the second term, since the operation or the sign here is negative, so take note to come up with the grouping symbol, minus, you will have here 1 cubed over 3 minus 0 cubed over 3, just to be mindful of the sign. And for the last, plus 1 minus 0. So again, 0, that's 0, this is 0. What we'll have here would be y squared, then you have here minus 1/3 if I'm correct, and we have here plus 1, or just combining them, you will have here 2/3, right? 1/3 or negative 1/3, and then you have 1 is of course obviously 2/3. This is now the function we're going to plug in here for this integral sign and the remaining sign notation dy. This would be, again, the boundary is 0 to 2 now, 0 to 2, and you will have here y squared plus 2/3, you have your dy. You could see that your first process is correct once you would notice that for this function here, it will no longer contain x. It would either contain y or just constant, just like this one here. So by linearity property, allow me to place it here. You will still have here 0 to 2 of your y squared dy because that's with respect to y now. But the second one would be 2/3. You have your dy, dy 0 to 2. Let's integrate them. For y squared, we know that's actually y cubed over 3 from 0 to 2. This is now 2/3 of your y, integral of dy, from 0 to 2. Okay? Hopefully the space are enough here. Allow me to use the boundaries now. You have 2 cubed over 3 minus 0 cubed over 3. Plus the other one is 2 cubed times 2 minus 2 cubed times 0. We know this to be 0. This as well. That's 2 cubed is actually 8/3 plus 4/3. That's 2/3 times 2. This is actually equal to 12/3, or basically 4. This is now the answer or the value to the given integral here for our functions along your smooth path C using the Green's theorem, using the components of your partial derivatives in this region as well. So try to verify this if you're going to use again earlier the dy, exchanging this one here, if you will get the same answer, because I guarantee you that actually they will have the same answer, provided that we will have the same idea here that our x and y are very simple in both vertical and horizontal perspective. Thank you very much for watching.